Hello everyone, welcome to my video. In this video, I'm gonna talk about the non-uniqueness of the multiplicative decomposition, that is f equal to fe times fp, where the two bars denote that f is a second-order tensor, and e denotes that it's the elastic part of the deformation tensor, and p denotes that fp is a plastic part of the deformation gradient tensor. This is motivated by a comment from Avinash that he suggested me to talk about the intermediate configuration of the process, and in addition to this, I would also mention the rigid body rotation. Finally, I will discuss the non-uniqueness of the multiplicative decomposition. Okay, first, let's consider a material that at initial configuration and we name them as S0. And if we apply a deformation, that we would get the material in the so-called current configuration. And we name this as CC for C current. Because of this deformation process, we can use a deformation gradient tensor f to denote this process. And this is a physical problem. And if we do a thought experiment, we can separate the elastic deformation from plastic deformation. Even though this is not practical, but let's just do this thought experiment. So first, let's apply a plastic deformation associated with Fp. So we get another configuration, and this is the so-called intermediate configuration. Alright? And after this, we apply a pure elastic deformation associated with Fe. Oh, one more thing is that let's recall the definition of deformation gradient tensor. That f is defined as partial h over partial uppercase of h here. The one bar denotes that h is a vector, and here this smaller case of h is the element in our current configuration. And this blue color in the uppercase of h denotes that the element in our initial configuration. And we also introduce another element that h hat with a hat, that this is the element in yellow color, in the intermediate configuration. Alright, so with all of this, let's start our work. Okay, so basically from this figure, we can see that if we do the elastic unloading from the current configuration, we unload it, we get this intermediate configuration associated with this. That means because there is no elastic deformation in the intermediate configuration, so the stress is zero, because the stress is only contributed by the elastic strain, plus the strain does not contribute for the current stress. So the intermediate configuration is a stress-free status. And because of this, as we can understand this intermediate configuration as it corresponds to elastically unloaded material, so it can be obtained physically through elastic unloading of the material. But remember, this is not practical, because if we unload the material from Cc to Ci, from current configuration to intermediate configuration, there must be stress associated in practice. But here, in a dot experiment, we treat it as stress equal to 0. Because of this, we got this intermediate configuration. So, what we can write is that we have an element in current configuration is equal to a deformation tensor times the element in reference configuration. And further, this deformation gradient tensor can be read as a partial derivative of x in current configuration with the derivative with respect to uppercase of x in reference configuration times the x here. And this can be, and because of chain rule, this part can be read as this. Times uppercase of x. Remember that this x with hat denotes the element in our intermediate configuration. Because of this, recall this FP and FE. So we can further write this equal to, so because this is from, so this term is from current configuration to intermediate, is the deformation gradient tensor between current configuration and intermediate configuration. So this is FE times, similarly this is FP times the uppercase of x. And if we write this out, that we combine this with this together, we get this: the lowercase x, the uppercase x equal to Fe times Fp. And where this derivative equal to f initially. So now we get this multiplicative decomposition for this process, and this can be decomposed into elastic part and plastic part. Okay, so now we will discuss more on the non-uniqueness. So the non-uniqueness is because of the rigid body rotation. So what is rigid body rotation? Rigid body rotation is the random rotation, to say, of the material. And for an objective stress and objective strain, there's no stress and no strain induced in that rigid body process. But because of the definition of deformation gradient tensor, recall that a displacement vector is defined as this, right? This is for in current configuration, this is in reference configuration. And so to the derivative, we have this. So this is f. So we have f equal to partial u partial x plus I. So from this we can see that even though the strain and stress is 0, but the displacement is not necessary. To be 0. So for rigid body rotation, f, the deformation gradient tensor, is not equal to identity tensor. So because of this, for rigid body rotation, we define FR, a rigid body rotation part for the deformation gradient tensor. So that means for general deformation process that it's f equal to Fe times Fp. But actually a more general expression should be we add fr here, or here, or even here. And sometimes we can also partially separate fr equal to, equal to fr1 and fr2 times blah blah blah. So we can put them in different places. So basically what I'm saying is that this process this multiplicative decomposition is not unique, and we have infinite numbers of possible combination of this deformation process. I think because of this that I've illustrated the non-uniqueness. So because of this, that this we can say that f equal to fe1 fp1 equal to fe2 fp2, that fe1 generally is not necessarily equal to fe2, and fp1 is also not necessarily equal to fp2. Right. Even though some people prefer to put the rigid body rotation part into the elastic deformation, and some of them prefer to put them in the plastic deformation. This is just up to your preference, and also for the specific problem. Okay, now let's have a summary. So basically what we did is that we consider a material. It deforms from the initial it deforms from the initial configuration to current configuration through a deformation gradient tensor, and this process can be separated by applying the plus deformation first, and then apply the elastic deformation. Of course, this process is not possible in practice, but we just do this in our thought. This is a thought experiment. If we can do this, that we can unload the material from configuration to our so-called intermediate configuration, and all the elastic deformation will be removed. So ideally, we will have this stress-free configuration, but actually it's not. But in our thought experiment, it is. Because of this, that we get this intermediate configuration, and usually we prefer to work in this configuration. So for this whole process, we can write this. Consider an element in current configuration and consider an element in reference configuration. We have this deformation tensor to link them, and this deformation tensor can further write like this. And if we use the chain rule, we can write this in terms of the intermediate configuration, and we can recognize this as the elastic part of deformation gradient tensor, and this as plastic part of the deformation gradient tensor. And also we recognize that this together is just the deformation gradient tensor. So we get this multiplicative decomposition of this deformation process. Recall that this is the definition for displacement is equal to the displacement is equal to the current configuration minus the reference configuration. So we have deformation gradient tensor defined in terms of displacement, the derivative of displacement in term with respect to reference configuration, and plus identity tensor. So that means for rigid body rotation, usually the displacement u is not equal to 0 usually. So that we have this deformation gradient tensor is not equal to the identity tensor, and we further name this the deformation gradient tensor associated with the rigid body rotation. We name them as FR. So for for general deformation process with rigid body rotation, this decomposition is not total deformation process. We can put FR here, 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 or within FP or within FE. Because of this decomposition is non-unique. And some of the people they refer to put the rigid body rotation part in the elastic part, and some of them prefer to put the rigid body rotation part in the plastic part. This is just up to personal preference. If you have any questions, please leave a comment, and also comment on what you would like to see in the future. If you enjoyed this video, please click the thumb up and like it. Also share with your colleagues. Alright, with all of this, see you next time. Bye.